All right, everyone, welcome back to the land of Chem. I am your host and the author. My name is Jeffrey Drum. Thank you all so much for joining me again.
All right, everyone, welcome back. Now, today we are going to venture even further into the depths of the mechanisms of operation driving the Egyptian pyramid chemical engineering systems, with an evaluation of the temperature and pressure conditions that can be achieved inside the primary steam reformer of the Red Pyramid. Ladies and gentlemen, as always, thank you all so much for the support. I think that is it for today's intro, so without further ado, let's get right to it. All right, everyone, here we go with tonight's episode. Now, to begin, before we proceed with this mathematical analysis revealing the physics-based reaction chamber conditions inside the Red Pyramid's primary steam reformer, as I was preparing for this episode today, I stumbled across this article by Alexandre Kasyanchuk entitled "The Egyptian Pyramids Start Making Sense," discussing my work, and Kasyanchuk is a PhD in both physics and mathematics, and this article specifically focuses on extolling the virtues of my research on the Red Pyramid, and I will quote here, "I came across a remarkable explanation from Jeffrey Drum on YouTube of the Egyptian pyramid's purpose. He nailed it. In short, each pyramid was a chemical plant, with various pyramids producing various chemicals. For example, he suggests that the Red Pyramid was built as a plant that produced ammonia from methane and nitrogen." Next, he also corroborates my hypothesis on the function of the step pyramid, stating here that Drum compares the chambers in the Red Pyramid and in Fritz Haber's process, provides chemical analysis of the residues in those chambers, discusses pressure and temperature conditions for the chemical processes. Pyramids retain gases and water in tunnels and chambers under high hydraulic pressure needed for chemical reactions, and he suggests that the main source of methane was natural gas, and according to the European Space Agency, Egypt, especially in the area around the Nile River, emits a lot of methane. Exactly as I proposed in episode 125, the function of the step pyramid evolution for the extraction of bedrock deposits of methane gas. He then goes on to describe the pressure conditions and capabilities of the reaction chambers within the Red Pyramid, the primary subject for today's episode. Again, all of this coming directly from a PhD in both physics and mathematics. But that's not all. In his article from the Daily Plasma blog, engineer Andy Hall, contributor to the Electric Universe and Thunderbolts project, describes my hypothesis regarding megalithic chemistry, and I'll quote a few things here. First, Drum presents a thesis that the ancient structures were chemical processing plants used to produce chemicals for solution mining and crop fertilizer. How mundane, yet sensible. The ancients weren't communicating with aliens, spirits, stars, or the dead, but were actually making nitrates to fertilize their crops and acids to solution mine and process precious metals. Of course they were, just like we do and every other society one cares to look at throughout history. He backs his thesis with on-site investigations to confirm predicted channels, passages, chambers, and other features for fluid flow, pressure control, and containment in the Egyptian pyramid temple complexes. Trace elements from these processes are even identified. Furthermore, I believe, this is a quote from Andy Hall directly, that he is substantially, if not wholly, correct. In my former career, I built and operated cogeneration power plants integrated with a variety of chemical processes and visited too many refining, processing, and manufacturing plants to count. So Andy Hall is a qualified engineer who had a career building and operating cogeneration power plants that integrated a variety of chemical processes. And he resumes stating here, "I know a process when I see one." Drum identifies precisely the use of chambers, passages, tunnels, and even the choice of rock used in a construction and how it integrates into an overall process flow. He identifies the chemistry, the process, and the system's integration, as well as the products and the purpose. The products and purpose make perfect sense in growing an agricultural empire, and the use cases justify the expense, unlike any other theory ever presented. The integrity of his work is in identifying how the pieces and parts worked together. They worked like chemical plants do today, mixing and reacting, settling and separating, transferring aqueous solutions here and there. The vessels they used were stone, not steel, but the processes were no different. He provides common sense, holistically viable, technically verifiable answers. This dramatically separates his from any other theory. He also correctly identifies the power source that ran the processes: nature's electricity, lightning, and telluric currents. This is another reason I know he's right. He's the only theorist who doesn't lose his mind and go extraterrestrial when it comes to the energy source. He understands it comes from the earth. No aliens were needed. Drum's examination is primarily of the Giza plateau and its pyramid complex and certain standing stone sites in the UK and Europe, but I contend his model will apply throughout time and geography across most, if not all, megalithic sites, because it provides the simplest, most verifiable answer that fits with the needs and capabilities of those cultures. It's a theme repeated at every site one can consider a cradle of civilization. Occam's razor will prove Drum right. End quote. And if you haven't seen it yet, Andy also made a fantastic video breaking down the various hypotheses presented in my book and here on the channel, entitled Megalithic Chemistry, that is now available on the Thunderbolts Project YouTube channel. And after a serendipitous series of events, Andy and I have finally gotten in touch, and you can anticipate some groundbreaking collaborations coming up soon. These are just two examples of the overwhelming support that I have received from qualified individuals from both the academic and professional fields, ranging from physics and chemistry to electrical engineers and petroleum geologists, and the list goes on. So Alexandre and Andy, from the bottom of my heart, thank you so much for your encouragement and support. And I'll put links to both articles and the video in the description below. So now, ladies and gentlemen, with that being said, let's turn up the pressure and the temperature inside the first chamber of the Red Pyramid, otherwise known as the primary steam reformer. And within this chamber, a reaction occurs between methane and water that produces hydrogen and carbon monoxide, as I explained in episode 156, by the following procedure. Step 1. Fill the chamber with water until the connecting shaft between the first two reformers has been filled. This isolates the space within the primary steam reformer and sets the initial pressure and temperature conditions within the chamber. Next, the methane fill process is initiated, and the methane gas, which is lighter than air, will flow into the chamber and rise into the upper reaction vault. This process continues until the reactor is filled with methane gas. Next, the water level inside of the chamber is increased further, compressing the methane gas into the upper reaction vault, gradually increasing both the pressure and temperature. This process continues, utilizing the water to compress the methane further into the reaction vault like a plunger or piston, pushing up on the gas, further increasing the temperature and pressure within the system. The water level is raised until it has reached the 7th tier in the reaction vault, and the reaction between the methane and water producing hydrogen and carbon monoxide will proceed, bringing us to this stage here, with the compressed hydrogen and carbon monoxide syngas in the upper vault of the first chamber. Now, before we get to the math, a quick announcement. My Brainstorm podcast with Ben and Finn is now available. Ben is a physicist, and Finn is a science author, and both are contributors to the Electric Universe and Thunderbolts Project. This is an absolutely fascinating conversation discussing a variety of aspects of my work, and my appearance on the Osiris Project channel also just premiered, featuring an in-depth analysis of the Userkov Pyramid with one of my colleagues and an original member of the Osiris Project, who participated in their epic expeditions to Egypt from 2010 to 2013, whose chemical analysis data will be coming up later in this video. So please go check these out and subscribe, as I will be doing follow-up interviews on both channels, links in the video description below. All right, now, buckle your seatbelts, as the true capabilities of the Red Pyramid's reaction chambers are about to be revealed, with calculations showing the temperature and pressure conditions that can be achieved inside of the primary steam reformer. Starting here, with the total volume of the chamber, with the query, calculate the volume of the first chamber inside the Red Pyramid of Dashur. And you can see I've included the entire chain of information if you want to pause the video and read all of the details. So the total volume of the first chamber is estimated at 384 cubic meters. Next query. Okay, now, please calculate the volume of the upper 7 feet inside of this same chamber. And this upper 7 feet of this reaction chamber is a critical detail that I will be coming back to again soon during the episode focusing on the pump shaft and the external reservoir.
All right, everyone. I hope you're enjoying the video. And please remember to subscribe for more content if you're interested in the technology of ancient civilizations utilizing physics and chemistry and the function of the Egyptian pyramids and other ancient structures from around the world. If you want to help support the channel, you can pick up a copy of the Land of Chem book and grab some merch at thelandofchem.com and for access to exclusive content. Subscribe to the members-only channel now with 19 massive research episodes revealing some of my most groundbreaking discoveries thus far. Links to everything in the video description below. Thank you all so much for the support. Now, back to the video.
And we have the full volume calculations and considerations here, with the final answer estimated at 20.3 cubic meters for the upper 7 feet of the primary reaction chamber. Okay, now, so we have our initial volume, 384 cubic meters, and our final volume, 20.3 cubic meters, V1 and V2. All right, next query. Please calculate the temperature and pressure changes in the following adiabatic compression system, with initial temperature 25 degrees Celsius, initial pressure 1 atmosphere, initial volume 384 cubic meters, final volume 20 cubic meters, and the gas is methane. So now, what happens to our starting temperature and pressure? I'll walk you through all of the calculations so you can see each figure step by step. Beginning here with initial temperature, T1, 298.15 Kelvin. Initial pressure, P1, 1 atmosphere. Initial volume, V1, 384 cubic meters. Final volume, V2, 20 cubic meters, with our gas, methane. So methane is a polyatomic gas with a specific heat ratio of approximately 1.31 at room temperature. Next, the adiabatic process equations. For an adiabatic process, the relationships between pressure, volume, and temperature are as follows. Next, our temperature and volume equation here, solving for the final temperature. So step 1, we will calculate our volume ratio with the initial volume and final volume giving us a ratio of 19.2. Step 2, calculate the final pressure using our specific heat ratio for methane of 1.31 and the calculations here with the final pressure P2 coming out to 47.963 atmospheres. 47 atmospheres final pressure. Step 3, calculate the final temperature, T2, again using the specific heat ratio for methane of 1.31 with the calculations here. Temperature 2, final temperature coming out to 744.74 Kelvin. So our final answer for these adiabatic compression of methane calculations, final pressure approximately 47 atmospheres, and final temperature approximately 471 degrees Celsius or 744.7 degrees Kelvin. Now, let me read that one more time and let this sink in for just a minute. The final pressure achieved inside of the primary steam reformer of the Red Pyramid is almost 48 atmospheres. And the final temperature in that same chamber is 472 approximately degrees Celsius. Absolutely staggering. Next, I ran the same calculations again with a slightly higher starting temperature, as it can get pretty hot inside of these chambers on the average day, this time starting at 30 degrees Celsius, with a bit more compression, this time into the upper 19 cubic meters. So we have 5 degrees Celsius more starting temperature and 1 extra cubic meter of compression. Now what happens? Final answer, final temperature 604 degrees Celsius and final pressure of 37 atmospheres. So in this scenario, we have slightly higher final temperature and slightly lower final pressure than the first calculations. So just for fun, I took the average of these two data sets and came up with a final reaction temperature of 538 degrees Celsius and a final reaction pressure of 42 atmospheres. 538 degrees Celsius and 42 atmospheres of pressure, which takes us once again full circle back to episode 27, the function of the pyramid body, with one of the primary justifications for the massive core of stones surrounding the reaction chambers being the containment of the tremendous internal pressure within the system. Now, the next series of calculations. Query here: what reaction happens between water and methane at 538 degrees Celsius and 42 atmospheres? And I'll quote here: at 538 degrees Celsius and 42 atmospheres, the reaction between water and methane is most likely to proceed via steam reforming of methane, a well-known industrial process, with the reaction as follows, exactly as I've described: methane plus water equals carbon monoxide and hydrogen. The key points regarding the thermodynamics and catalysts stated here. The reaction is endothermic, favored by high temperatures like 538 degrees Celsius. High pressure, 42 atmospheres, shifts the equilibrium to the left, but the temperature is sufficient to drive the reaction forward if catalyzed. Regarding the catalysts, this reaction typically requires a catalyst to proceed at significant rates under these conditions. Well, it just so happens that these reactors are teeming with catalyst material, as you will see in just a moment. And a final note here regarding the practical context: these conditions are milder than the typical industrial steam reforming that occurs between 700 to 1,000 degrees Celsius at around 20 to 30 atmospheres, but still feasible for partial conversion, especially with a catalyst. But there is also something very special that happens to water under these same conditions that will also facilitate this reaction sequence. So what happens to water at 538 degrees Celsius and 42 atmospheres? At 538 C and 42 atmospheres, water is in a supercritical state. Water exists as a supercritical fluid, neither distinctly liquid nor gas, with unique properties like high density and high diffusivity. This state is often exploited in industrial applications like supercritical water oxidation or power generation. So what happens between water and methane at these same temperature and pressure conditions? At 538 degrees C and 42 atmospheres, water is in a supercritical state and methane is a supercritical fluid or gas-like state. Under these conditions, the reaction between water and methane is primarily governed by steam reforming. Again, the primary reaction being steam reforming of methane. The most likely reaction under these conditions that we have achieved within the first chamber of the red pyramid, the most likely reaction is steam reforming, where methane reacts with water or steam to produce carbon monoxide and hydrogen. Again, the thermodynamics, this reaction is endothermic and favored at high temperatures like 538 C. The equilibrium shifts towards the product of carbon monoxide and hydrogen due to the high temperature. The pressure effect at 42 atmospheres, the increased pressure slightly disfavors the reaction because it produces more moles of gas. However, the high temperature dominates, still driving the reaction forward. And last but not least, regarding the supercritical water state, supercritical water enhances reaction rates due to its unique solvent properties, high diffusivity, and ability to dissolve organic compounds like methane, creating a homogeneous reaction environment. Ladies and gentlemen, the truth shall set you free. And I will quote one more time here, the expected outcome of these temperature and pressure conditions within the first chamber of the red pyramid. The primary products are carbon monoxide and hydrogen via steam reforming, with possible traces of carbon dioxide from the water-gas shift reaction. The exact product distribution depends on the methane to water ratio, the presence of catalysts, and residence time in the reaction environment, i.e., the longer it sits in the chamber, the more conversion of the products are achieved. The math speaks for itself, and the reaction chambers of the red pyramid have been precisely engineered to produce the exact temperature and pressure conditions to drive this reaction without exceeding operating temperatures that will damage the internal limestone blocks. This will be coming up again in part 3. But as always, ladies and gentlemen, this is just physics and chemistry 101. So what about the catalyst material that really pushes this reaction forward? And what if we were to introduce electric fields into this system? Let's start here. Scale up studies on electrically driven steam methane reforming. This work is devoted to scale up parametric studies of a new reactor system for the steam reforming of methane driven by electrical current. The main distinguishing feature of this type of reactor is the use of direct electrical current flowing through metal particles to heat the whole reactor volume. Well, it just so happens that we discovered 39 different types of metal particles inside the reaction chambers of the red pyramid, which also contains nickel, the main catalyst utilized in the methane steam reforming process. And I'll quote from this article here, Improving Nickel Catalysts Using Electric Fields, a DFT and experimental study of the methane steam reforming reaction. This work demonstrates the benefits of applying an external electric field to the methane steam reforming reaction in order to tune the catalytic activity of nickel. Through combined DFT calculations and experimental work, we present evidence for the usefulness of an electric field in improving the efficiency of the current methane steam reforming process, specifically lowering the overall temperature requirements. So, by introducing electric fields and effective catalyst materials, the activation temperature of the methane steam reforming reaction can be decreased below the 700 to 1000 C of conventional reformers, temperatures that would not be sustainable within these limestone chambers. And remember from episode 108, electric fields inside the Great Pyramid, that the Egyptian pyramids are literally designed to concentrate both electric and magnetic fields. As revealed in this paper here, electromagnetic properties of the Great Pyramid, first multipole resonances and energy concentration, showing the concentration of electric and magnetic fields surrounding the primary reaction chamber of the Great Pyramid. And in episode 117, I explained the roles of electric fields in driving chemical reactions. As best summarized in this article here, electric field intensified chemical processes and reaction chemistry. Stating here, electric fields represent an important resource that can be utilized for process intensification in the chemical industry. Utilization of electric fields provides an efficient and cost-effective way for intensified chemical processing and reaction chemistry. And it turns out that electric fields can also be applied to the methane steam reforming reaction. So remember that we have already achieved temperature and pressures within this reaction chamber that will produce the reaction between methane and water, creating hydrogen and carbon monoxide, with temperatures around 811 Kelvin. The addition of catalysts like nickel, which I have just shown are present inside of these chambers, and electric fields would just be icing on the cake to further increase the percentage of conversion, improving the efficacy of the reaction. So remember, we have 811 degrees Kelvin inside of the primary steam reformer chamber. Check this out. Support effects on catalysis of low temperature methane steam reforming. Stated here in the abstract, low temperature, less than 500 Kelvin methane steam reforming in an electric field was investigated over various catalysts. Catalysts which include cerium oxide. I'm sure you can already see where this is going. And this reaction can be achieved at less than 500 Kelvin, and we have 811 K plus catalyst. Next, this article here, low temperature hydrogen production by catalytic steam reforming of methane in an electric field. Stating here in the abstract, catalytic steam reforming of methane in an electric field, otherwise known as electroreforming, at low temperatures such as 423 K was investigated. 423 K methane steam reforming. And one more article here to really drive this reaction home, entitled Low Temperature Steam Reforming of Methane Over Metal Catalyst Supported on Cerium Zirconium Oxide in an Electric Field. Again, from the abstract here, catalytic steam reforming of methane in an electric field named electroreforming was conducted over metal catalysts supported on cerium oxide and cerium zirconium oxide at low temperatures such as 423 K, where conventional catalytic reactions hardly proceed. The conversion of methane was greatly increased by weak and effective application of an electric field to the catalyst bed. Oh, cerium and zirconium catalyst, you say? Don't tell me. That, of course, both cerium and zirconium were discovered in the chemical analysis data from the metal staining inside of the red pyramid. And I'll be coming back to the role of these electric fields and catalysts later when we reach the reactions within the final synthesis chamber and the low temperature strontium catalyzed ammonia synthesis reactions that were presented in episode 152. So now that I have shown that this reactor can achieve the temperature and pressure required to produce the methane steam reforming reaction, and that we have evidence of the exact type of catalyst that we use today, including nickel, cerium, and zirconium, let's take a look at how the reaction process moves into the secondary air reformer. So we concluded the last episode with our product syngas of hydrogen and carbon monoxide in the upper vault of the primary steam reformer. Now, at this stage of the reaction, there is also water in the northern pump shaft, and we'll be coming back to this later in a focused episode on this series. And you can see here, at the bottom of the secondary reformer on the south side of the chamber, this shaft. Another never fully excavated shaft that is now completely covered by the modern wood plank flooring inside of the chamber. This shaft is the drain shaft utilized in this series of steps. So here I've added the drain shaft, and we will lower the water level inside of the chambers through this drain shaft that will first start pulling water from the secondary air reformer, dropping lower and lower, and will then drain water from the primary steam reformer. And as the water level in the primary steam reformer decreases, the gas will adhere to the surface of the water, aided by the high pressure within the chamber and surface adhesion between the gas and water. Remember, surface adhesion. Adhesion is the tendency of dissimilar particles or surfaces to cling to one another. And as the water continues to drain in this direction, moving south toward the drain, it will eventually drop below the level of the connecting shaft, creating an aperture between this high pressure system and this low pressure system, through which the gases can flow into the secondary air reformer. So we have three factors at play. First, surface adhesion between the gas and the water. Second, the south directional flow of the water moving from chamber 1 into chamber 2. And third, the pressure differential between the primary steam reformer and the secondary air reformer, all three of which will facilitate the movements of gases in a south direction, moving from chamber 1 into chamber 2, and the hydrogen and carbon monoxide, being lighter than air, will flow up, rising into the upper reaction vault of the secondary air reformer, leaving us at this stage here, with the hydrogen and carbon monoxide syngas in the upper reaction vault of the secondary air reformer. And before we conclude with today's episode, allow me to introduce Exhibit A. This image showing the southern wall of the primary steam reformer and the clear flow dynamics pattern indicating the movement of gases exactly as I just described, flowing from the upper vault of the primary steam reformer through the connecting shaft into the secondary air reformer. And as I said in part 1 of this series, the red pyramid is the smoking gun of this ancient pyramid chemical engineering technology, displaying not only evidence of the fluid dynamics of this manufacturing process, but demonstrating the physics and mathematical capabilities that are engineered into the tiered vaults of these chambers. These structures were designed to communicate exactly how they operated. By reducing volume, you increase temperature and pressure. And by a simple process of detailed examination, reverse engineering, and mathematical calculations, the bewildering temperature and pressure capabilities of this chemical reactor system have finally been revealed. All right, everyone, that is it for today's video. This was episode 157, the temperature and pressure conditions inside the Red Pyramid's primary steam reformer. I really hope you enjoyed today's video, and in the next episode in the series, Sunday Site Visit 102 with a highly anticipated on-site expedition. This is an episode you do not want to miss, so if you haven't already, please subscribe to The Land of Chem here on YouTube, and remember to click that little notification bell so you don't miss out on the new episodes that premiere twice per week. Please like, comment, share. Stay tuned. If you want to help support the channel and get access to exclusive research, check out the Land of Chem members only channel and thelandofchem.com. If you want to pick up a copy of the book or grab some merch, both linked in the video description below. If you want to follow me on Instagram or on X, my handle is @thelandofchem. Also, don't forget, after you finish watching this video, please go subscribe to our other channels, Ancient Odysseys, Let's Go with Lex and G, and the best channel on YouTube, Egyptian Trash Cats, for all you cat lovers out there. Also, all three linked in the video description below. Ladies and gentlemen, as always, thank you all so much for the support. think that is it for today's episode. I will see you next time. Yo, are you still watching this? Please subscribe to the Land of Chem here on YouTube and click that little notification button. New videos coming out every single week. And check out this other episode. Come on, do it. Do it now.